How's it going, you guys? So for this video, we're going to go over the problem Koko eating bananas. This is a binary search type problem, and it's been asked at Airbnb significantly. So without further ado, let's get into it. So the description says Koko loves to eat bananas. There are n piles of bananas. The ith pile has piles I bananas. The guards have gone and will come back in h hours. Koko can decide her bananas per hour eating speed of k. Each hour, she chooses some pile of bananas and eats k bananas from that pile. If the pile has less than k bananas, she eats all of them instead and won't eat any more bananas during this hour. Koko likes to eat slowly but still wants to finish eating all the bananas before the guards come back. Return the minimum integer k such that she can eat all the bananas within h hours. So I know that was a mouthful, but essentially we need to do this using a binary search. So what we're asked to do is to optimize our k, where k is the number of bananas that Koko can eat, and she eats these bananas every hour. So if we look at example 1, we have piles 3, 6, 7, and 11, and all of these numbers represent the number of bananas in that pile, right? And then h is obviously the number of hours. And so for every index, which is a pile of bananas, whenever Koko eats however many k we allow her to eat, then that will take 1 hour. And we want to minimize it. We want to have the smallest k, the smallest number of bananas that she can eat all of the piles, but in the smallest amount of time that's below h. So let's jump over to the whiteboard and I'll show you guys how to solve this, and it'll start making more sense. We're going to go over the first example that LeetCode provides. So we have 3, 6, 7, 11, and these are the piles. And then we have to make sure that Koko can eat all of these piles in less than h time, which is 8 in this case. And so before we get into the binary search solution, I just want to walk through a very simple example showing exactly what we have to do. So let's say we were to have Koko be able to eat 5 bananas per hour, right? This is just an arbitrary number. How long would this take her? So what we have to do, we have to iterate over all of our piles and determine how many hours it will take. So let's start at the first pile. And so our first pile has 3 bananas, and we're allowing Koko to eat 5 bananas per hour, right? Since the number of bananas that Koko can eat per hour is greater than the pile we're currently looking at, that means it will take her only 1 hour to eat this pile, right? Because for every index, for every pile that Koko lands on, it will take her 1 hour to eat her k bananas, right? So this would take 1 hour. And then we're going to move to the next pile, right? And so now we have 6 bananas. And so this would take her 2 hours, right? Because if we did 6 minus 5, right? Because she ate 5 bananas out of the 6 bananas in the pile, she would have 1 banana left. And so she would have to take an extra hour to eat this very last banana. So this would take her 2 hours, right? And then we're going to do the same thing. We're going to go to the next pile. She has to eat 7 bananas in this pile, but she can only do 5 bananas per hour. So if we did 7 minus 5, we still have 2 bananas left, right? But since our k, 5 is greater than 2, this would take her another 2 hours to finish this pile. And then finally, we're going to go to the very last pile. And once again, we're going to do, if we did 11 minus 5, right? We have 6 bananas left. And so this took her 1 hour to do. And then if we did 6 minus 5 again, we have 1 banana left. This took her 2 hours to do. And then this very last pile would be just 1 banana left. So this would, in total, take her 3 hours, right? And so if we sum up all of these numbers, we get 3 plus 2 is 5. 5 plus 3 equals 8, And so what that means is we found a k number where Koko can finish all of the piles in a time that is less than or equal to h, which is the time when the guards will come back, right? So 5 is our answer so far, right? But we want to optimize this. We don't know if this is the best answer. And this is where binary search is going to come into play, because we're going to try to minimize this k as much as we can. So in the next example, I'm going to go through a full walkthrough of the binary search solution. Okay, so we're going to go over the same example, just using binary search now. And for a binary search, we need a couple of different variables, right? We need a left and right variable, and this is going to be the bounds in which we're looking in this specific range, right? So we'll have left and then right. But what should these be initialized to? And so our left needs to be the minimum number of bananas that Koko could possibly eat. So this is going to be 1 banana, right? It's not going to be anything less than that. If we were to allow Koko to eat 0 bananas potentially, then she would never finish the pile. So the minimum k value would be 1. Because remember, these left and rights, they're technically the k values that we're eventually going to return from our function. And then our right is going to start at the very maximum of whatever is in this pile. So in our case, the maximum number is 11, right? So right would start at 11, because the most amount of bananas that Koko should eat is whatever maximum number is in the array, right? And so now we're going to perform the very similar logic to what we just did in the first example, except we're just going to perform our binary search to where if the hours that we calculate is less than or equal to h, then we are going to decrease our range down. So our right range will now become our mid. And then if the hours that we calculate is greater than h, then we're going to optimize it by moving our left towards mid so that we can get higher, right? So let's start doing that. If we said our mid is going to be left plus right divided by 2, like a normal binary search, right? That would be 6. So let's count how long it would take if Koko were to eat 6 bananas per hour. So we're going to start at 3, right? And so since 6 is greater than 3, that's only going to take 1 hour, right? We're going to move to the next one. We have 6, and 6 is equal to 6, so it's only going to take her 1 hour to eat that whole pile. We're going to shift over again, but now we have 7 bananas in this pile, right? So if we did 7 minus 6, we have 1 banana left, so this took her 1 hour. But then we have 1 extra banana here, so now it's going to take her 2 hours to eat that extra banana. So to eat 7 bananas took her 2 hours. We're going to move to the next one. And once again, we're going to do 11 minus 6, right? That's going to equal 5. So this took her 1 hour. We have 5 bananas left. And so this will take her another hour to eat the rest of the bananas. So this takes 2 hours to eat 11 bananas. So then we add up all of these hours. So that's 2, 4, 6, right? And since the number of hours it took is less than or equal to h, that means we need to decrease our right pointer. Because remember, we're trying to optimize k. We know that this value 6 worked, but we still want to try to get to a better solution. So now we can set right equal to whatever mid minus 1 is. So now our right becomes mid minus 1. So this is going to become 5, right? Our left stays the same. And then our mid is going to be left plus right divided by 2. So 6 divided by 2 is 3. So now we're going to see how long it'll take Koko to eat 3 bananas per hour, right? So we're going to do the same thing. We're going to start at our first pile. 3 is equal to 3. That's going to take her 1 hour. And then right here we have 6. So if we did 6 minus 3, that equals 3. So this took her 1 hour. Then we do another 3. This took her another hour. And then we have 0 bananas left. So in total, it only took her 2 hours. Go to the next one. 7 minus 3, we have 4. That took her 1 hour. 4 minus 3, we have 1. That took her another hour. And then we have 1 banana left. So it's going to take her another hour to eat that last banana. So we have 3. And then we're going to go to the last one. 11 minus 3, that's 8. Took her 1 hour minus 3. We have 5, another hour minus 3. Another hour, and then we have 2 bananas left. So another hour to eat the last 2. So we have 4 here. And then we add up all of our hours. So that would be 3 plus 3 is 6. 6 plus 4 is 10. But the number of hours that we have here is greater than h, right? So what that means is we need to increase the number of bananas that Koko needs to eat per hour. Because at 3 bananas per hour, Koko was not able to eat all of the piles in h time, right? So we need to now increase our left pointer to close that gap. And so now our left is going to move to mid plus 1. So our mid was 3, so now our new left will be 4. And then once again, we're going to do the same thing. 4 plus 5 is 9. 9 divided by 2 would be 4, right? And we're going to do the same thing. We're going to iterate on the first pile. 4 is greater than 3. That'll take 1 hour. And then I won't do the subtraction because I think it's understood at this point. So to eat 6 bananas, this would take her 2 hours. To eat 7 bananas, this would take another 2 hours. And then to eat 11 bananas, this would take her 3 hours, right? And so we sum up all of these once again. We get 3, 5, 8. Right? And so that works. That means 4 was a good K value because Koko ate all of the bananas less than or equal to H. So that means we need to decrease our right pointer because we're still trying to optimize. And so now we just need to move our right pointer down. So our right pointer will now change to mid minus 1, which is 4. And now we did left plus right divided by 2. That would also be 4. And as we already just calculated this mid, we ended up with a total hour number of 8, right? And so since we have to decrease our right pointer again, so this 4 would change to a 3. When our right becomes less than our left, that means we're done. And whatever the value of our left pointer is, that would be the optimize K. So essentially from this function, we would return 4. So next, I'm going to jump into the coding portion, and I'll show you guys what this looks like. So for a binary search, we need to initialize our left and right pointer. So let's do that. We can say int left is going to start at 1, and our right will need to be the maximum of what is inside our piles array. So we can say arrays dot stream of piles dot max dot get as int. And then we're going to perform our binary search. So we could say while our left is less than or equal to right, then we need to calculate our midpoint. So we can say int mid is going to be L plus or left plus right minus left divided by 2. The reason why we write it this way is so we can handle overflow. If we were to just do left plus right divided by 2, if left and right were very large numbers, those integers could potentially overflow and break our code. So that's why we write it this way. And so now we need to check if this mid value that we just calculated, if this is less than or equal to h, because this will tell us whether we need to shift our left or right pointer. So we can have a helper function for this. So it'll look like this. We'll say, if can eat in time, and we'll pass in our piles array, we'll pass in our mid, and we'll pass in h, right? So if Koko can eat this many bananas, mid bananas per hour in less than or equal to h time, then what that means is we need to decrease our right pointer to optimize to a better solution. So we would need to shift our right pointer to mid minus 1, right? So right would need to be equal to mid minus 1. If this is not true, then what that means is we need to increase our left pointer, right? So left will be equal to mid plus 1. And then by the end of this binary search, we're just going to return left because our left pointer will hold our optimized k by the end of the binary search. And so now all we need to do is just implement this helper function can eat in time. So we can say private boolean can eat in time. We're going to have piles. We will have will be our actual k value. And then we have h, which is the number of hours that we have to do it in. And so we need to have some way to keep track of a count of hours. So let's initialize a variable. We can call it hours. And then we need to loop over all of our piles. So we can say for pile of piles. And so now we need to actually perform the calculation to see how many k we need to be greater than or equal to the pile. So to do this, we can just do simple division and modulus operations. So just to make sure we understand what I'm about to do, let's say our k value was equal to 4. And then let's say that our pile, the current pile we're looking at, is 10, right? So for Koko to eat all of those bananas with k per hour, 4 per hour, that would take her a total of 3 hours, right? So this would take 3 hours. So to perform this calculation, we could do the pile divided by k, right? Because if we did 10 divided by 4, that would be 2, right? And that would be 8 total. So she would eat 8 bananas in a total of 2 hours. But then if we did pile mod k, the remainder after we did division would be 2. And so what that tells us is that we have 2 bananas left over, and we need to have another hour to eat the remainder of these bananas. If this value was 0, then we would not have to take an extra hour, right? So hopefully that makes sense. And I'll write the code now. So we'll say int, and we're going to do the division. So we're going to say, we can say div equals the k, or sorry, pile divided by k. And then we're going to do hours plus that division operation. And then we need to actually perform that modulus check. So if pile mod k is not equal to 0, that means we need to take an extra hour to eat the remaining bananas. So we can just plus hours. And then, since we're returning a Boolean, we need to see if this hours that we have calculated is less than or equal to h. So we could say return hours less than or equal to h, right? And so that's it for this code, actually. So let's just make sure that this actually works. So let's submit it. And there we go. So next, I'm going to jump into the time and space complexity of our solution. The time complexity of our solution is going to be n times log of m, where n is the number of piles that we have, so specifically the length of our piles array, and then m is the range of k, so specifically from 1 to the very maximum pile that we have. And this would be inclusive, right? And this is because in this while loop, we're doing this binary search, so from line 9 to 16, and that is where the log of m comes from. But then for every midpoint, every k that we're checking, we have to loop over all of our piles. And so that's where the n comes from. And that's why they're multiplied, because they're nested. So n times log of m. And then our space complexity is constant. We don't initialize any extra memory in our algorithm. So that's it for this video. Thank you so much for watching, guys. Feel free to like and subscribe if you like my videos. Yeah, laters.